Hello and welcome back to episode 8 of Polynomials. Today we're going to be looking at examples of using the cubic formula. So our first example we're going to look at is x cubed minus 15x minus 126, let's say. I'm going to draw that 6 again. And of course it's equal to 0. So first of all we look at p to get an indication of how many solutions we are wanting. So, because p is less than 0, we're looking at 1, 2, or 3 real solutions, which I admit is very helpful, very helpful. If we look at the discriminant that we learned last time, we find that q over 2 squared plus p over 3 cubed with the substitutions of minus 15 as p and minus 126 as q is equal to 3,844, which is positive. So therefore we will have one real solution. I'll just write that as one real. Okay, so plugging this into our formula, we put minus 126 in as q and minus 15 in as p, and we go down. What's interesting to note about 3,844, our discriminant, is that that is actually a perfect square. It's actually 62 squared, so that works out very nicely. So we in one bracket we have 62 plus 63, and in one we have 63 minus 62, which just gives us 125 root 125 plus root 1, and both of them are perfect cubes, and that will just give us 6, which is our only real solution. I won't show you how to get the other real solutions, but that's a challenge you can try once you finish this video. Our next cubic that we're going to look at is this one here, x cubed minus 6x minus 4. So first we look at p, and that will give us 1, 2, or 3 real solutions. But if we look at our discriminant here, it shows that this is actually all equal to minus 4, because the first little bracket here is just minus 2 squared, which is 4, and the second bracket here is minus 2 cubed, which is minus 8. So what we've got is 4 minus 8, which is just minus 4. And that tells us we have 3 real solutions. Of course, we get a complex number occurring because we have a negative number in the square root, but that is what we're dealing with this episode. So, putting in the numbers, we have 2 here, because that's negative q over 2. And we have minus 4 in here, and we have 2 minus 4 in here. And now I'm just going to replace that with complex number notation. And to do that, we just remember that root of minus 1 is termed as I, and therefore root minus 4 will just be root 4, or 2, times root minus 1, or I. So we'll have 2 minus 2i and 2 plus 2i in the second one. Moving down, so first, how are we going to do this? We're going to try and work out an algebraic method of solving for the cube roots of these two complex numbers. So let z equal a complex number a plus bi, and what we're going to say is that z cubed is equal to 2 minus 2i, because we want to find out what z is, and it would be quite nice if we could just cube root z cubed and we'd get z. So we're going to say that 2 minus 2i is equal to a cubed plus 3a squared bi plus 3ab squared plus bi cubed. Now I'm going to write that 3 again, I'm sorry. I am just cubing this number you see here. And that is equal to a cubed plus 3a squared bi minus 3ab squared, because I squared is just minus 1, minus b cubed I. And that will just equal, we're just going to pair the imaginary coefficients and the real coefficients together. That will just equal a cubed minus 3ab squared plus I times 3a squared b minus b cubed. And what we're going to do now is we're going to compare coefficients, because we have one real component and one imaginary component, same as the number we're trying to be equivalent to. So we say that 2 is equal to a cubed minus 3ab squared, and minus 2 is equal to 3a squared b minus b cubed. Now, it doesn't look like we're getting anywhere, because this cubic we have here is actually more complicated than the original cubic we were trying to deal with, the x cubed minus 6x minus 4. So what I've inadvertently done is led you down a rabbit hole, and we're going to have to try another method. This happens a lot in maths, where you go down one route thinking it might work, but you're not sure, but you have to try it. So you go down that route, it hasn't worked, and we're just going to have to try another route. Luckily enough, there is another route we can try, and that's modulus and argument form. Now, if you remember in the types of numbers video, I may have talked briefly about the Argand diagram and having an imaginary axis and a real axis, and complex numbers being denoted by a radius and an angle theta, a radius from the origin. The radius can be calculated because all we have here is just a right angle triangle involving A, B and R. So the radius is simply square root of a squared plus b squared. That's fairly simple. That's just Pythagoras' theorem. Or the Gogu theorem, if you really want another name for it. The angle theta can then be calculated using tan, because we have opposite and we have the adjacent side. So we can say that tan theta is equal to b over a, and therefore, I'm just going to write this below the axis, we can say that arc tan b over a is equal to theta, which is equal to the argument of our number z, or our complex number. I'm going to write the complex number symbol here then. Going down, we have let z cubed equal 2 minus 2i. I've redefined z now. So therefore the radius is going to be the modulus of 2 minus 2i, which is just the square root of 2 squared plus 2 squared, which is just square root of 8, which is the same as 2 root 2. Argument of z cubed is equal to arctan b over a, which is arctan minus 2 over 2, which is the same as arctan of minus 1, which is just minus pi by 4. I should say that when working with complex numbers, we always work in radians. If you haven't encountered radians before, don't worry. Pi is just the same as 180 degrees. So, the next thing we need to look at is we say that z cubed is 2 root 2, so r, times cos theta, which is cos minus pi by 4, plus I sine minus pi by 4. Now, the clever thing we can do with modulus argument form is to cube root, we just divide we just say that the modulus, the radius, is just the cube root's radius cubed, if that makes sense. So we multiply the modulus and we add the arguments. So we can just divide the arguments by 3. So we say that z is therefore equal to root 2, because root 2 cubed is 2 root 2, cos theta, which will be minus pi by 12, because pi by 4 over 3 is pi by 12. So minus pi by 12, plus I sine minus pi by 12. Then we're going to let m cubed equal our conjugate number, because we had 2 cubes. We had two cube root signs, and inside we had 2 minus 2i, which we've said is z cubed, and we've got 2 plus 2i in the other one, which I'm denoting m cubed. So r is the same, it's root 8, which is equal to 2 root 2, and then arctan 1 is the same as pi by 4. Now we can write this as our complex number. We can say 2 root 2 times pi by cos pi by 4 plus I sine pi by 4. And then we can say that m is equal to cube root of 2 root 2, which is just root 2, and pi over 4 divided by 3, which is just pi by 12, plus I sine pi by 12. Our first solution to our equation, x1, will be number z plus number m. So before I tell you that, the first thing we're going to look at is what do the graphs of cos x and the graphs of sin x look like. So cos x looks like this, because it's called an even function because it's symmetric about the y-axis. What this really means is if we have pi by 4, which is around here, it is the same value as minus pi by 4, which is just here. So we can say that cos minus pi by 4 is equal to cos pi by 4. It's an even function, so the minus sign doesn't make a difference. Sin x is said to be an odd function. And what this means is that if we have pi by 4 here, which comes up here, pi by 4 minus pi by 4 comes up with a negative value. So we can say that why am I using cos? Sine minus pi by 4 is equal to minus sine pi by 4. Because it's an odd function, we can take the minus sign out of the sign. Then we said that x1 is m plus n, so we add them together, and you'll notice that I haven't written anything to do with I sine. That's because if we look back up at our original thing that we're adding together, the plus I sine pi by 12 will cancel out with the minus I sine pi by 12, because we've taken out the minus sign here, we've taken out the minus sign there, put it there, and then we can cancel with the other sign. So we have no complex part left. That's where the complex part goes, the imaginary part. And what this leaves us with is we have our answer is simply 2 times root 2 cos pi by 12, which is just 2 root 2 pi by 12, which is just equal to 1 minus root 3. I'm just going to check that on my calculator. So cos pi by 12 is equal to that, multiplied by 2 root 2 is equal to 1 plus root 3. 1 plus root 3. Our next answer, we just add 2 pi by 3, or 120 degrees, to our original angle. Because this is how you find the complex conjugates when you have 3 roots. So what this will be is minus 2, and then we do the same thing again, and we get 1 minus root 3. So there we get 3 real solutions from a seemingly complex start. Thank you very much for attending this episode on cubic examples, and I look forward to seeing you all next time.